Hello everyone. Today we will talk about the learning steps that are involved. So I guess previously you must have heard from Professor Tanmoy and others about the architecture uh, of these models, and today we will talk about how to train these architectures. And specifically, we are interested in constructing something like ChatGPT, and what are the different steps that go about in constructing something like ChatGPT. Okay. Uh, So there are three main steps that are there. The first one is pre-training, which is the most important step. Pre-training simply means that you collect as much data that you can get your hands on. So here we are talking about large language models, so language data probably, as much language data that you can get your hands on. Probably scrape the web to get all the HTML web pages that are there. Uh, you get billions of tokens of unstructured text, and then finally you train the model, train your whatever your LLM architecture is. Here we are talking about transformer LLM architecture, and just train on top of these web pages that you have downloaded from the web. So this is the most important step, and this is the step where most of the reasoning power will go into your model. uh, the later steps will be about how to make these models more friendly to humans, but those steps do not insert as much reasoning into the model as this pre-training step. So if your model is not pre-trained very well, any step that you do in the later steps like instruction tuning or reinforcement learning, none of this is going to actually none of this can make a badly pre-trained model work. So pre-training step is the most important step. The second step, and this is what we'll talk about today, the second step is the instruction tuning step. And in instruction tuning, basically now we are going towards making these models behave better for human, because you have pre-trained the model. It will have a certain behavior, but it won't make sense to human. For it won't make sense very easily for human. So how to make these models makes more sensible towards humans is you make them follow instructions. So in instruction tuning, you have instruction and you have output. Like you give the instruction sort these numbers, and the output is a sorted list of numbers. Uh, so you have several thousand of these instructions and task instruction and output triplets, and you train your pre-trained model on top of these instructions. This is what we'll talk about in the next class. And finally, the third step that goes into making something like ChatGPT is the reinforcement learning from human feedback. And this is the part where humans directly interact with the model. You show the output of the language model to humans and ask them, okay, do you prefer this output or this output? Now, why do we need this step? Because even if you have instruction tuned the model, its output may not be desirable to humans. For example, it might still generate abusive content, or it might generate content in the format which humans don't like. For example, humans might prefer list or a certain structure of the output. So to make the output desirable to human, you actually show that output directly to human. You say, okay, what is the preferred output? Collect feedback in the form of preferences, and then you use these preferences to further improve the model. And in this case, the data is that you require is your instruction and task, and you need either a human being or a reward model, or you construct a reward model from human being. This is what we'll see in the later class. We'll discuss about how these information from is used to improve the model. So in today's class, we will focus only on the pre-training aspect. And as I mentioned, this is pre-training aspect is the most important part of creating a good model. So why do we need pre-training? So I guess you must have talked, Professor Tanma must have talked about BERT earlier, right? So before the BERT was there, people didn't, or before Elmo was there, for example, people didn't give any importance to pre-training. So the uh, the reason why we need pre-training is that if you look at human beings, they are very good at generalization from very limited examples. You show them 4 examples of a task, and you ask them to solve the 5th example, and they will be able to solve it. Like if I show you this example, this particular example where the input is CAT and the output TAC. And if I ask you, what would be the output if I give you DOG as input? So everybody can answer it, right? What would be it? GOD, right? It's just the reversal of the characters. And now humans are automatically very good at it. You see in one example, and you can immediately judge what is happening in this example. But before this pre-training era and before, in fact, GPT-2, this idea that you can learn from a very few examples, like even one example in this case, is the idea was not very popular. So the reason why humans can do it is because we have accumulated a huge amount of knowledge over past several years, and that knowledge helps us to understand what the underlying task might be. And that is what we want to feed inside the model. We want to feed this accumulated knowledge of human beings inside the model, so that when I give a new task, it can understand from a very few examples what the underlying task is. So the question is, how do we do this? How can we use this vast amount of data that is there on the web and improve the performance and get a model that can generalize better from very little data? Okay, so before we get into pre-training, let's talk about the generative model for sentences. Previously, Professor Tanmay must have talked about BERT, which is also pre-trained, right? Okay, so you have a transformer encoder, and which takes some input tokens and generate input tokens, basically input embeddings, and generate some output embeddings, and you train it in a masked fashion. So by masking, I mean you mask some of the tokens at the input, and you should be able to reconstruct those the tokens that you masked in the output. The question is, can we use is BERT is a good choice for generative modeling of sentence? What do you guys think? It's I guess the answer is also here. The thing is that it's not a generative model. What I mean by that is that there is no straightforward way to generate a sentence from a BERT model. There are multiple ways you can define a generative model, but it does, first of all, it does not assign probability to a sentence. You cannot assign probability to a sentence using this model, and there is no straightforward way to generate. You can use it for learning sentence embeddings and such. Okay, so what can we do? So by generative model for sentence, what I mean is a model from which we can sample the sentences. And here we will be talking about probabilistic models. So if I give you any sentence which is a sequence of tokens, and the probability of any model can be any probabilistic model for over sentence can be written in this form. This decomposition has nothing to do with the model assumption. This is true irrespective of what you want to do. You can always decompose the joint probability distribution in this form. So this probability of a sentence is probability of token 1, this is the token 1, times probability of second token given the first token, and so on and so forth. Token 2 given token 1 times probability of token 3 given token 1 and token 2. So if you can multiply the probability to get the probability of an entire sentence, and this decomposition holds true irrespective of the model that you assume. Our aim is actually to parameterize the distribution in this way. What does that mean? That although any probability distribution can be decomposed in this format, getting this form is not easy for most distribution, but we can define a distribution which computes the probability in this way. Like it computes the probability of the tokens one by one. So probability of token 1, it computes first, and then probability of token 2 given token 1, it should be able to compute it this way, right? And each of these PIs that you see here, these are distribution over the vocabulary. Okay, so these are they are not. I mean, vocabulary size generally around 50,000 or 100,000 or something like that. So these distributions can be thought of as vectors of dimension 50,000 or 100,000. So they are easy. My point is they are easy to sample from. Okay, and if these if your model can be if these PIs are provided to you, or the parametric form of these PIs are provided to you, that okay, this is how these PIs look like, then we call such a model as an auto-regressive model. This is an auto-regressive model. So again, any distribution can be written in this form, but generally these PIs are not easily computable for most distributions. But if you can decompose your distribution nicely with nice values of PIs, then it's called an auto-regressive. Okay. Basically, you compute your model is easily able to compute the distribution in this form. So if you have, so why do we care about this auto-regressive model? Why not just some arbitrary distribution. Why? What is so special about auto-regressive? The first thing is it's very easy to sample from such a distribution. Why? Uh, your distribution is in the form of P1. So you can, if you want to sample a sentence, what you will do, you will pick the first of those distributions, P1, and sample a token from P1. This is easy, right? A multinomial sampling, I'm guessing everybody was really familiar with it. You just pick a token from the distribution P1, and now you uh, feed the token into P2 and ask it to predict the distribution over the next token and sample the second token from that. So, and then you can sample subsequent tokens condition on all the previous tokens, and this gives you a very nice way to sample the tokens in a text. This is very difficult to do for something like images, because images can have millions of pixels. But for text, which has like 1000 tokens or something, this is a very easy thing to do. And that's why these auto-regressive models are extremely popular for text compared to any other distribution. All right. So what should these PIs look like? Okay, let's make this picture more concrete. Till now we were talking about abstract distributions over vocabularies, and now we want to make this more concrete. So specifically, think of an encoder, not very dissimilar from the BERT encoder. Right now, if you want as a picture, you can think of the BERT encoder. It takes these tokens, beginning of sequence, first word, second word, third word. It takes the embeddings and computes some form from transformation. It can be any transformation. It can be an RNN, it can be a transformer, or it can be any architecture. And it finally gives you some embedding. This is the output embedding that we have. And then it applies a projection layer. This W can be thought of as a projection layer. And what this projection layer does is that it takes this embedding and gives you a probability distribution over the tokens. So now, in order for this distribution to make sense, we have seen that P1 can only depend on, actually P1 cannot depend, P1 cannot condition on anything. So beginning of sentence, you can think of that this is a fixed, you can think of this as a parameter. This is not a token. As I mean, intuitively, you can think that this is just a parameter of the model, right? So P1 cannot depend on any of these tokens. It has to actually depend only, it can only get information from this part of the network. What we are trying to do is construct an auto-regressive distribution. So it has to get information only from, it cannot depend on any tokens of the sequence. Okay. Now P2 can depend on the first token, which is, this is, I mean, let's ignore this. Let's call this as T0 for now, and this can be fixed. P2 can depend on till everything that comes from here. Similarly, P3 can depend on everything that comes from this part of the encoder. And P4 can have the entire sequence, everything here as input. Okay. Is there any question about why this distribution? Because you are trying to construct a probability model, and you have to you're forced to factorize the this is one of the possible factorization that you have to use here. Okay. So given this factorization, what are the possible encoders that I can use here? Now that I know that P1 has to come only depend on the BU as the beginning of sequence token and so on, what are the possible encoders that I can use here? So one possibility is used to use something like RNN, a recurrent neural network, and a unidirectional RNN can be used here without any issue. Why? Because unidirectional RNN already has that property that the embedding embedding at the tth time step, or the jth embedding only is a function of the previous embeddings. Okay, so if you the information, if you look at this H3 does not get any information from H4. Okay, so H3 is only or from the word, then H3 does not get any information. So H3 only has information from the first 3 tokens, and so it satisfies our criteria that the information that is reaching for P3 only has information from the beginning of sequence token, the first token, and the second token. It does not have any information from the future token, right? So that's a good it's a good architecture that satisfies our criteria. But there are problem with the RNA encoder. The first problem is, if you look at how Hj plus 1 is computed, it's a function of Hj and the token at the time step, the jth time step, Tj. So if you have to compute the hidden state of all the n tokens, how much, let's say there are m tokens, and you have to compute the hidden state of all the m tokens, how much time will it take? Yeah, it will be proportional to m, right? So time is the proportional to number of tokens. And if you're dealing with very small sequence like 20 words, 100 tokens or something, this is fine. But generally, you will be dealing with 2048 tokens or even 4096. Nowadays, people even talk about 100,000 million tokens. And you cannot afford to have that many time steps of computation for getting the embeddings, right? So this is why RNNs have already been discarded. So we don't want this sequential computation of embeddings. How do we get rid of the sequential computation? That's what our task is. So we want to be able to satisfy that criteria that Pj should only depend on the tokens before jth time step, but we also want to get rid of the sequential computation, and that's where this architecture of transformer is very interesting. It's a revolutionary architecture because it satisfies all of the criteria. So first let's look at a BERT type architecture where every token. So this is a transformer encoder. I'm guessing everybody is familiar with the transformer encoder, right? And this is a full transformer encoder with full attention mask. What that means, that every token can attend to every token. And what it means in otherwise, that information from every token can flow towards every embedding. So E2 gets information from all the tokens, E1 gets information. So each of the distribution is able to see all the tokens. So can we use this particular encoder for our task for learning auto-regressive model? Right? It does not satisfy our criteria that P3 cannot look at T4 and P2 cannot look at T3 and so on. It does not satisfy this criteria, right? So what can be done? So we want to make sure that P1 only does not look at any of these tokens. So P1 can look at this, that is fine, but it cannot look at anything else. Similarly, P2 can look at beginning of sequence as well as the, but nothing else, right? And the P3 distribution can look at the first two distribution. So we need to somehow modify this transformer so that they can only look at tokens. The jth distribution can only look at tokens till jth time step. And such an attention mask, I will construct that in mask. Such an encoder is also referred to as decoder. So you can say that there is not much difference between encoder and decoder. It's just a decoder has this causal attention mask, that the jth distribution only depends on the previous tokens. Whereas if you are talking about encoder, generally we talk about fully attention mask, right? So such a mask is called causal attention mask, and I will draw a picture of it here. So if you can write the tokens here, this is how a causal attention mask will look like. It will have basically it will make sure that no token can look at its future. They can only look at themselves or look at their past. I guess causal attention masks have been covered, right? So, okay. So okay, so this is how the architecture should look like. What should be the loss function? So this is a quick recap of maximum likelihood. If you are given a parametric family of probability distributions and you are given some n observations from a particular distribution, these should be independent and identically distributed from some unknown distribution PD. And if I ask you, okay, given these observations, find the best parameter theta star that can explain these observations. That would you want to find p theta star that will maximize the probability of these n observations. So then you want to find the parameter theta that would best explain these observations. So what you will do, you will define the joint probability of these n observations, p theta s1 to sn. This is the joint probability distribution. And then what you will say is that, okay, this the argmax of some function is the same as the argmax of the log of that function, so you can just add log here. Okay, and because these observations are independent, you will decompose it as a product. The joint distribution will decompose as a product, and since it is inside the log, the product will become a sum of log probabilities. So this is your maximum likelihood estimation. Given any observation, any parametric model, find the parameter that maximizes this quantity. That's your maximum likelihood estimate. So if you have, so in our case, the observations are sentences. So the probability of a sentence can be decomposed into the probability over the tokens. Right? This is the probability of the first token, and this is the probability of the each subsequent token. And each of these are parameterized by theta. Let me, if you want, I can put a theta here. This you can assume that this theta is I removed the theta for the sake of convenience for now, let's say. And so the log probability can be decomposed over the tokens also. Note that the tokens are not independent, although the sequence, the observations are independent. The tokens here are not independent. So don't. So tokens are not observation. The sequence, the entire sequence is one observation. Okay. And if you want to do maximum likelihood estimation, what you will do is you will just try to find the parameter theta such that it maximizes the log probability over the summation s belonging to d log probability theta of s. Or let's put the length of the d also. This is your maximum likelihood estimate. Okay. Is this clear? Okay. So far, I have not talked about anything which I'm guessing is some you guys are not already familiar with. It's maximum likelihood estimation. Okay, so now let's move to the pre-training part. This was more of a recap towards how you will construct a generative model for sentences. Now, how do you do pre-training? Now that you know how to construct a generative model, how would you do pre-training? So yeah, so for pre-training, you need to make some considerations. First of all, you can only pre-train if you have a huge amount of corpus here, and a huge amount of corpus generally available on the web. You can collect, you can use common crawl or many of the other web crawls that are there, and then you have to curate and filter it, which we will talk about in the next slide. The next thing that you need to consider is what tokenizer to use, what is the vocabulary size that you want to use here. People use vocabulary around 50,000, between 50,000 and 100,000. Depending, if you are using non-multilingual, generally 50,000 vocabulary is good enough. If you are using multilingual, you might need more, like 100,000. And for tokenizer, people use different sorts of tokenizer, like byte pair encoding and all. I'm guessing they are also covered. Yes. Okay. Then you have to decide what is the model architecture you need. Obviously, if you're doing pre-training, that means you are going to use transformer, because it's not possible to do this large-scale pre-training with any of the RNN or LSTM-based approaches. They are the computation will be just too extreme. So if you're using a transformer, you have to decide what are the number of layers that are there, what is the dimension of the token that you want to use, what is the hidden dimension that you want to use in the transformer. People generally keep them similar, like token dimension as well as hidden dimension are generally assumed to be same. Then you also want to decide the number of attention heads that are going to there in each layer. And finally, what is the maximum sequence length that you want the model to support? Or there are two parts here. Maximum sequence length that you want the model to support for inference or for pre-training. They can be different also. If you are using something like rotational embeddings or something, they can be very different. So for example, people can allow inference for any number of tokens, but for pre-training with, let's say, 4096 tokens. that's also a possibility. And lastly, you want to consider whether you want to use which optimizer you want to use. Generally, people don't use SGD. People use any of these Adam, AdaGrad, AdaFactor optimizer for the for optimization. And what are the hyperparameters of the optimizer? Like what is learning rate? What if you're using Adam or AdaGrad or AdaFactor, you will also have this beta parameter that you have to decide. So all these considerations need to be made, and each of them will, if you will can I mean, is a different topic altogether. But this is just an overview of what all considerations go about for someone who wants to pre-train a model. Okay, so for one of the steps, the first step is actually data curation and data filtering. And generally, what is done is that you scrape the web, or you use already somebody's data somebody who has already scraped the web, like Common Crawl, for HTML documents, for text documents. If it is an HTML web page, you want to extract the content from the HTML web page, so you will use some parser to remove HTML tags and give you the content part of it. Then you also want to do deduplication, because you want to ensure that the same data does not occur multiple times. You also want to remove non-informative documents. What this means is that there will be a lot of log pages that are there on the web. People might have run some experiment, generated some log, pushed it on the web. There might be a lot of error messages that will be there on the web. So those are not something that have any informative content. It's there, and non-informative content is actually bad for the model. If you tell the model to maximize the probability of something, some error tokens or something, and that error token is very repetitive, what will happen is that model might forget its original behavior of language modeling and might start generating pure generating pure noise actually. You also want to remove outlier documents. So if a document has a token distribution which looks very different from anything that is there in the rest of the corpus, you also want to remove those. And optionally, you want to train a classifier to determine the quality of the document. Yeah. Okay. So let's look at tokenization. So for pre-training, so everybody is familiar with tokenization. You take a document, apply a tokenizer, you will get a list of tokens, and you append an end of text token at the end of it. This is a list of tokens. And then you have an end of text token after that. So, but when you do pre-training, what you do is something very interesting. You take all these tokenized documents, and you create a long stream out of these documents. So why do we do that? So during pre-training, actually, we never use padding. Let me write this down. No padding. So you create a huge chunk, and now you have already decided your sequence length of training, let's say 4096. So what you will do, you will randomly pick the first token, randomly pick, let's say let's call this a token K, and then token K plus 4096. And you will assume this to be one giant sequence of 4096 and feed it to your model. That's it. So from here till here, everything is fed into a sequence. So all the sequence that are being fed during pre-training have the same length. All right. Okay. And then you do maximum likelihood training that we've already seen. Okay. All right. Let's see now what pre-trained models can do and what they cannot do. Okay. So what are pre-trained models good at? So now we are going towards more. Now we have a pre-trained model. We are going towards the behavior of these pre-trained models. So they can mimic the behavior of the data that they have been trained on. And many of the data that you feed to these models will have these almost supervised examples. Even though you have scraped from the web, they will have these examples. For example, if you can see, this is from the GPT-2 paper. I'm not the cleverest man in the world, but like they say in French, something, which is in, the same sentence in French. So the model already has some understanding. It has learned those relationships. Okay, that if this comes in the input, this is these kind of sentences are likely in the output. It has learned this behavior. So so if you ask it, okay, here is a poem that describes the sun, blah 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 blah, as it gets dipped in chocolate, and you give a first sentence of it, it might be able to complete the poem. Okay. Uh, so you need so actually to get some interesting behavior out of these models, you need to do some work, because they're not trained for. I mean, they're not directly usable by random human. You'll have to modify your prompt so that it becomes usable by this model. But if you, let's say, give it, just say write a poem that describes sun getting dipped in chocolate, it will not generate anything meaningful. It will just start keep on completing it. It should be a haiku. It should be about sun getting. It should be a haiku. Blah 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 blah. But it's not going to generate a poem. Can anybody think why it's not generating a poem? Why it's not following the instruction, even though I gave it? Yeah. Yes. Yeah. So generally, the data on the web, right? It's not in this clean format that you have an instruction and you have an output, right? It's just a bunch of, for example, some of the data might be question papers from some exam, right? Just questions. Now, if you ask a question, what do you expect it to generate? It will generate the next question. It won't generate the answer. If you, it will keep on generating questions and questions and questions. You can force it to generate answer by giving some part of the answer. Okay, the answer is we can go on blah blah blah. Give some prompt, and then you can expect this model to complete the rest of the answer, right? And so this is a problem that most of the training data is not in the instruction format that you want it to be. So how do we make them work? There are two possible directions. First is in context learning, which is what we'll discuss in today's lecture, and the second is instruction tuning, that we'll see in the next lecture. Okay, and both of these are emergent properties. You guys were there in the last class, so if you guys were there, you might know about emergent properties, which is properties that occur uh, at a certain time. They're almost non-existent below a certain number of training flops, and they appear suddenly after a training flop. So instruction tuning, for example, here on the graph that you see, instruction tuning behavior was around, performance was around, I'm guessing this is some sort of 40, the score was 40 on some task, or 45, and after, as soon as you jump from 10 to the power 22 to 10 to the power 23 training flops, suddenly the performance went to 70. So instruction tuning is an emergent property. So if you take a smaller model and force it to follow instruction, it will not follow instruction whatever you do. Okay, it will not have this instruction following behavior, arbitrary instruction. uh, uh, so a large model trained on large data for enough time steps can exhibit instruction tuning behavior, where you tune it for a following instruction, it will start following instruction. Similarly, in context learning is an emergent property, that if you have a small model trained on small data for a small number of training flops, it cannot do in context learning, but a large model with a large number of data and a large number of training flops can you can expect to see to do in context learning. Okay, so let's talk about in context learning. So what is in context learning? That the in context learning is basically you have a query that you want to solve it, and you have some similar examples that whose input are also similar to what your query is. You feed it with the query. So let's say you are doing sorting of numbers. You give some example of, okay, this is the unsorted list, this is sorted list, this is unsorted list, this is sorted list. Create some examples, and then you give your unsorted list. Then the model will be able to understand what the task is that you are expected to solve, and it will exhibit the task. So here, if you look, yeah. So if your review is good meal, if you just ask review is good meal and ask it to generate sentiment, it might not be able to do it. But if you give these examples, okay, review delicious food, sentiment positive, review the food is awful, sentiment negative, and so on, and then you finally you give your query example, review good meal, what is the sentiment? Then the model is expected that it should be able to extract what the underlying task is from these examples and be able to solve this task. Okay, so why do we need in context learning? We need it because if you have a pre-trained model, it's not going to follow your instructions. So you can either tune it for instruction or give it examples of the task that you want to solve, right? And here we're talking about how to give the examples of the task. So how can we improve? So this is simple, right? You have any task to solve, you bring examples of the task and give it with your query example and hope it can solve it. But is there some way to improve it? Can we do something either during pre-training or during inference so that I can improve the performance of this of in context learning? Okay, so injecting world knowledge that it did not that you did not give during pre-training during fine-tuning. What if we? Okay, that's fine. But generally during pre-training you give all. That's a good point actually. If you are, there's a domain, a medical domain or certain domain that was not given during pre-training, you can give it during inference. Okay, that's fine. That's one way. Uh, uh, Interestingly, what has been observed, so if you think what effectively happening during in context learning, you're giving examples of the same task and then you're expecting it to follow that particular example, right? So during pre-training, perhaps I can organize my data in that format that I will need during inference. So during inference you're giving multiple examples simultaneously, right? Maybe during pre-training I can organize my data in that same format. That okay, I have this task and I have similar example. I grouped all the, so for example, if in my pre-training data there is a document about sentiment analysis, I can find all other documents about sentiment analysis and group them together. And why is that helpful? Uh, the reason is that because this is the same format that you're going to use during inference, right? That where you will you are expected to give similar examples and follow the task from those examples. So this is one way. Okay, so if you want to improve in context learning, what you can do is you can organize your training corpus. It's very huge, it's difficult to organize, but let's say you could organize your training corpus so that documents that deal with the same task come together, and then you can take sequences across these documents. Okay, so this is one way. The other thing you can do is so this was during pre-training, by the way. So this is, but if you already have a GPT-3, you cannot do much, right? This is during pre-training. Now, what can you do during inference? So there are many of these things that people have tried. People have tried putting all sort of edge cases so that it does not deviate from those. It can learn the behavior without deviating much. This is one way, which is you actually embed the example that you want to do inference on, and so this is the embedding of the example. This is the embedding of the example, and then you look at embedding of other examples in the same space and find out these already have the label. These examples already have the labels, and you for these examples you take the input output pair and feed your query example and ask it to generate the output. Okay, and the logic is that if some certain example has an input which is close to your embedding, that means those examples might be more might guide the behavior of the LLM in a better way for X. So examples that are closer to my current query input are more suited for me. So this is a heuristic. It may not always work, and sometimes, but this is what you expected to. This is what people have tried. Does that make sense? Okay. Okay. So now, what is the notion? What similarity should I choose? So one thing people have done is that embed the inputs using a sentence encoder such as Roberta, and just measure the cosine similarity between your query embedding and the embedding of other examples. Is it? And you select the top key, whatever number of examples are needed, you select it and feed in context. What might happen is that if you select the examples based on similarity, cosine similarity, what might happen is that all the examples that you select are very similar, and that may also not be desirable. So food for thought, how can you make this set diverse so that not all the examples are same, right? You don't want all the examples that you feed to be same. So this is so far we have assumed that the similarity metric was learned in an unsupervised way, where you're not training the similarity metric, right? You're just taking something like a sentence embedded such as Roberta and just using it for your task, finding similar examples. But question is, can you actually train the similarity metric in a way such that the examples that help your model better are picked? Anybody think that can we train the similarity metric? So this is one approach for contrastive learning of the similarity metric, and the idea is that You use this unsupervised retriever. It can be BM25 or it can be your sentence embedding based retriever. You use the unsupervised retriever to get a bunch of examples. Okay, so here you have gotten some candidate examples, and now given for each of this candidate example, you compute a score. What I mean by score is you feed this candidate example along with your query example and along with your query, and remember this is training, so you also have the output for your query. And so one thing you can do is you can let me write you can compute the log probability of the ground truth output given x and all the other examples x1 y1. So this can be the score of example 1. Let me write this as score of x1 y1. Similarly, score of x2 y2 will be log probability of y given x comma x2 y2. So this way you can you're basically what it's capturing is that if I give the example 1 as input, what is the score of my gold output? If I give example 2 as input, what is the score of the gold output? And so now since you have a ranking, what you can do is contrastive learning. What contrast learning means is now what you will say is the let's say the example 1 has the highest score. Okay, let's say e1 equal to x1 y1 had the highest score, and en is equal to xn yn had the lowest score. So contrastive learning mean you will say that even should the embedding of x1 should be much closer to embedding of x, and embedding of xn should be far from x, right? So you can use something like a triplet loss to enforce this. Does that make sense? How basically contrastive learning of the similarity metric, forcing the examples that give higher score to be closer to your current example. Now we have seen how to make it work, contrastive learning, in context learning. The next thing is, why does it work? And there have been lots of papers to understand why this in context learning works. So let's look at these examples. So if you give as a prompt, apples are red, bananas are yellow, grapes are what, then it might print purple. But if you give lemons are sour, cranberries are bitter, and grapes are what, it might give sweet. So these in context examples are somehow guiding the model to generate either purple or sweet for the input grapes are. Both are valid outputs, but depending on what those examples are, it's generating either purple or sweet, right? So there are two popular theories about why in context learning works the way it does. And first is that it performs some sort of implicit Bayesian inference, and the second one is that it does gradient descent. So second one is what we will focus on, that transformers learn in context by gradient descent. Okay, so a quick recap on gradient descent. If you have some inputs x1 x1 y1 x2 y2 xn yn, and you want to learn a linear model between x and y, so what will be your loss functions? Can anybody tell me what the loss function will look like here if I want to learn a linear model between x and y? And let's call this loss as r theta. Then one can do gradient descent on this loss to basically reach in this case a global optimum, because this is a if you choose your delta t's appropriately, you will reach a global optimum here. Okay. Also a brief digression on linear transformers. So what is a linear transformer? So in a regular transformer, what you have is that you're embedding after attention, let's call it is computed like this: q k transpose upon the dimension of let's say the hidden size times some softmax into b, and there is some masking also here. So in a regular transformer, the output after attention looks like this, and in a linear transformer the softmax is not there. So just qk transpose over root d over v. This is how a linear attention will compute the output of a layer. Okay. So this softmax is what is missing from linear transformer, and basically it can compute linear functions of the input. That's the point. So the idea that transformers learn in context by gradient descent, what it means is that if you have a linear transformer with linear attention networks, then if you feed your input, let's say you train your transformer in this way, you feed the you take a bunch of examples xi ya and ask it to predict xn plus 1, so yn plus 1 for xn plus 1. So if you're doing gradient descent, what will you do? You will minimize the loss, find the optimal parameter, and then use the optimal parameter to predict yn plus 1, right? Now the claim is that transformers do it implicitly. If you so let's say you take a transformer, give them a sequence of demonstration x1 y1 x2 y2 and till xn yn, and train it to predict the correct yn plus 1 for so you train it with this training objective. Then implicitly each of these layers do a step of gradient descent. This is the interesting part, that although you're never training it to do gradient descent, but gradient descent emerges naturally in the layers of the transformers. So this is the result, that there exist stationary points of the training objective such that the prediction at layer k is the same as k steps of gradient descent. So the first layer does one step of gradient descent, the second layer does two steps of gradient descent with some particular appropriate delta values. Yeah. Okay. Finally, so what are the main takeaways here? First, we can create a generative model for sentence by using a causal attention mask in transformer. Second thing, in context learning is an emergent property, which means that you need large enough model, large enough data trained for sufficient amount of time for this property to emerge. And you can improve it either during pre-training by clustering similar data, or during inference by selecting examples that are closer to your query. And finally, in context learning implicitly performs some form of gradient descent. Okay, we can stop now.